Hello everyone, welcome to my presentation on enthalpy. So today is going to be a little review on the second part of enthalpy. We had already kind of discussed enthalpy and a couple of the applications in chemistry, and today we're going to talk a little bit about the second part. And here's just a little bit of an overview of what we're really going to be talking about today. So enthalpy is discussing the heat that is being released or absorbed during a certain process. And so if we remember, enthalpy just isn't the heat, but it also involves the work. And so we can say H is equal to E, which is equal to the internal energy, plus PV. And PV actually stands for the work being done. This is pressure and volume. This right here is equal to work done on the system as well. But in most of our circumstances and most of our examples, we're not going to be too worried about the work done on the system. But right now we're just going to be caring about the internal energy or the change of heat within the system. So today I just wanted to emphasize a little bit about how to calculate the enthalpies in a reaction. So there are three main ways that we can calculate the enthalpy in a reaction. The first is to sum all of the reactions and their enthalpies, and that'll give you the final enthalpy. The second is the enthalpy of reactants of the products, looking at really what is going on within that chemical equation and determining whether heat is released or absorbed during this process. And the third is that we can calculate it through bond enthalpies, the individual bonds within an equation. We can use those to determine the total heat that is released or absorbed during a process. Along with these things today, we're going to talk a little bit about fuel value and the difference between fuel value and fuel density, and kind of a couple I guess applications of both of those things. So like I said, there are three ways to compute the enthalpy of a reaction, and these are very, very important to remember. And when you run across them on the exam or wherever else we're working on them on tests or or homework assignments, when you come across a problem that asks to calculate the enthalpy or the heat gained or lost within a reaction, you should think about these three processes. And I like to kind of think of these as tools in our toolbox to really determine the enthalpy of the equation. So the first, like I already said, is the sum of reactions and their enthalpies. The second is the enthalpies of the formation of reactants and products within a reaction. And the third is to calculate the individual bond enthalpies, or the energy it takes to break and form those bonds. And so we're going to break this down just a little bit more. So talking about the sum of reactions and their enthalpies, I just kind of wanted to use a couple examples really quickly. So essentially, the first way to calculate the delta H, or the enthalpy in a reaction, is equal to the sum of all of the delta H's within a process. Etc. And so in this example here, I just kind of wanted to use a quick example. We can calculate the sum of the enthalpy for these three reactions. As we can see here, the first reaction releases 100 kilojoules per mole within the reaction. The second reaction releases 30 kilojoules per mole. And the third reaction releases, or actually gains, 320 kilojoules per mole. just a side note with this, it's important that you remember that this negative sign out front, this little negative, is very important when it comes to the reaction. This negative, when it's negative, that means that the reaction is exothermic, which means that it releases heat, releases energy during the reaction. And if it is positive, that means the reaction is endothermic. And these are both going to come into play as we kind of determine what the total enthalpy will be within a reaction. And so if we're not looking at this bottom part here with the letters, but if we look at this top part here with these three reactions, we can actually calculate the total enthalpy change within this reaction. And so why don't we do that here? So we have reaction 1, the delta H is negative 100 kilojoules. Oh, and actually, to be honest, this part here is incorrect with the moles. We can just assume that, oh, actually no, we'll leave it for now. For every 1 mole that this reaction undergoes, it produces 100 kilojoules of energy. We'll just say that. Or it releases 100 kilojoules of energy. Anyways, with reaction 2, delta H is equal to negative 30 kilojoules. And reaction 3 is equal to 320 kilojoules. And we can kind of see when we're looking at this reaction that this reaction is going to be overall endothermic when we look at all of the processes, because we can kind of see that in the end the total reaction is going to be positive. And so, like we know, we need to just sum up all of the enthalpies of this reaction. So we have a negative 100. We're going to add that with a negative 30. Sorry about that, I had to do a quick change of scenery, but right here, as I was saying, we had a negative 100 kilojoules. We'll put the units there to remember. Negative 30 kilojoules and a positive 320 kilojoules. And so if we want to find this sum, the delta H, we know that we can just add all of these together to get the final enthalpy. And so that's what I'm going to do right now. So we got negative 100 plus negative 30 plus 320, and that's going to give us a positive delta H. Let's see here. That's going to give us a positive delta, sorry, my stylus isn't working, positive delta H of 190 kilojoules. And so we know that this reaction is going to be endothermic, and that it's going to absorb energy. Alright, continuing on, I wanted to look at just a couple other examples here. So we know that just a couple pointers on just kind of some other reactions. Let's pretend like this little reaction here, just with the letters, is an actual reaction. Let's say that it releases 200 kilojoules per mole. As we can see, this second process is the exact opposite, right? It's just a reciprocal of that first process, and so we know that we can actually just flip this sign, and that for this second process, it will release a total of 200 kilojoules, and that's actually going to be positive. So this first one's negative, and the second one is positive. Another thought with all of these things when looking at the reactions, you can also add more than one reaction together. And let's say that there were 2 C's here, and that this released, or let's say that once again this released 200 kilojoules per mole. And let's say that this ran 2 times. Well, it's simple enough that you can actually just multiply this value by 2, and so your total released energy will be negative 400 kilojoules per mole. Or not per mole, but kilojoules released in this reaction. And so these are actually probably the most simple of the enthalpy equations because usually they're going to be given to you, and you can just analyze the amount of energy released and what you need to get to, and kind of use more algebra than anything else to get to your desired result. Okay, moving on just a little bit, we're going to talk a little bit more about the enthalpies of products and reactants. And so with this, the main thing that you guys always have to remember is that we need to remember that it is products, number of moles, products minus reactants. And then n number of moles of reactants equals our delta H. Okay, so this is really, really important. I think that we're probably going to see more of this on our exams than anything else. But let's dissect it just a little bit with these examples. And so as we can see with this first equation here, our products, we have 2C. I just used a random integer just because, just for an example here. But we have 2C, 4B, and 2A. Usually, our heats of formation are going to be given to us, and that's what is given down here. And you can actually just ignore these minus signs for now. We'll just say that they're all positive for now. Okay, so as we can see here, let's just remember, let's put it up here just so we don't forget, delta H is equal to n number of moles times products minus n number of moles times reactants. And let's just recap. These are products and these are reactants. So looking at this first equation, we can see that we have 2C, 2 times, and then we know, sorry, when I say products, I also mean the delta H of these products. And so using the indicated values, just right down here, we can come to the conclusion that the delta H, so these are all delta H's, of C, which is our product, is 309 kilojoules, right? And that's our only product that we have. And so we can just assume that delta H is equal to that minus our reactants. And our reactants in this circumstance are 4B and 2A. And so we come down to the table, we say, okay, A, we have 2 moles. Just to remind ourselves, 2 moles of A, which is 250 kilojoules. And then we're going to add that with 4 moles of B, which is 33 kilojoules. Great. And so just like before, it's just algebra after this. We'll go 2 times 309. And that's going to give us 618 minus 2 times 250, which is 500, plus 4 times 33. That's going to give us a 632. And so we know that this reaction in total is going to leave us with a negative 14 kilojoules of energy. And just like before, this value right here is negative, and so we can assume that this reaction is exothermic, right? Meaning that heat is released in this process. So I'm going to do one more example just so we can kind of see one more time quickly how it's done, and just kind of have one more quick observation on how we can really do this. Okay, so using the same table down here, we're going to do the second reaction. So in this second reaction, we have 23 moles of C. So we'll do it quick. So we have 23 moles of C, which is negative 309, actually positive 309, minus reactants. And with our reactants, once again, we have 3A, which is 250, plus, running out of room here, 6B, which is 33, once again. Great. And so once again, we just plug these numbers in. 23 times 309. That's 7107 kilojoules. Minus, then we're just going to add these two together again. 3 times 250 plus 6 times 33, 948. 8. And so we can just take these two numbers here, subtract them once again. That leaves us with a total delta H, which is positive, of 6,159 kilojoules. So we know that this reaction is going to be endothermic. Well, great. Okay, so moving on just a little bit, this is actually just a great graphic that I found online that I think could really help us out. But essentially, it just goes over exactly what we talked about. We have the delta H of formation of the products, all right here, because, this is a very important point right here. When looking at products minus reactants, whenever there is a single element bonded to itself, like an O2 or an H2 or any of these things, heat of formation in its standard state is always going to be 0. So delta H is equal to 0, always. Whenever we have an O2, N2, H2, the same element bonded to itself, that's always going to be a 0, and that's pretty important to remember, so we don't confuse ourselves. So, using this example, we have sucrose right here, the C12H22O11, mixed or combusted with oxygen, and this gives us CO2 and H2O, and a release of 285 kilojoules per mole of the H2O, 393 kilojoules per mole of the CO2, and so on. And so just like we did with those letter examples, they did the exact same. So we can see that they did products minus reactants. The two products being CO2 and H2O. So we know we can see the 12 right here from the number of moles of CO2 with the negative 393 kilojoules per mole right there. And we can see the 11 moles of H2O and the negative 285 kilojoules per mole right there. So this is a very important aspect to remember, because as we do products minus reactants, it's very important to remember the sign of all of these things. And we need to always remember that it takes energy to form bonds, and we release energy when we break bonds. And that's actually going to lead us into this next part very well. So the next part I wanted to touch on are the bond energies of enthalpy. And so I like to kind of think of it like we have all the reactions, then we have, or the sum of all the reactions, then we have the reaction itself, and then we have the bonds between the actual individual atoms. And so when it comes to the bond energies of enthalpy, we're going to go with the bonds breaking minus the bonds forming, in contrast to the products minus reactants. And so in this situation, with this example here, we can see that we have 2 moles of AB breaking, and that's a single bond, plus 2 moles, plus 1 mole, of CD breaking, and that's a double bond. And so we can see here that the double bond broken is 300 kilojoules. And then we subtract this value that we get here from the AD bond and the CD bond. So we'll do that right now. So 2 multiplied by the AB bond, which is 250, plus the CD bond, which is 300, minus, from here, the bonds forming. We know that these are the bonds breaking and these are the bonds forming, just by way of where they're placed on the reaction. We know that these are going to break apart and form these products here. Just to finish out this example, so we had the 300 from the bonds breaking, and we're going to subtract the bond AD right here, which is 260 kilojoules. And we're going to add that to the CB bond, which is the 200 kilojoules kGa. Great. And so we're just going to throw this in the calculator again. 2 times 250 plus 300. And then we're going to subtract 260 minus 200. And that's going to give us a positive delta H of 340 kilojoules. And so one other thing that's pretty important to remember is if we have a complex compound, we're still going to calculate all of the things broken. So if we have like a COOH or CH2 or CH3 bonded with a number of other things, we'll do an example here, CH3OOH. So we're going to calculate each of these bonds that are broken. And so it'll usually give us an OH bond with a enthalpy or a amount of energy it takes to break that bond. And in this case, we would multiply that by 3 to get our final result there. And so these are pretty simple as well. But the hardest part usually is going to be drawing out the Lewis structures and counting out all of the bonds that we need to break and all the bonds that are forming as well. Great. So kind of going back a little bit, what we need to remember when we're talking about fuel value and fuel density is that these are two different things, but are very, very crucial to not only chemists, but also physicists as well. And so the fuel value is the heat over the mass, and that's going to give us the fuel value. Whereas the fuel density is going to be our heat over our volume, and that's going to equal our fuel density. And so I have just one example I wanted to use here. So in this example, we see that a certain reaction releases 40,000 kilojoules of energy for every 300 kilojoules or kilograms of product. And so when we take the when we divide these two and we take the ratio, we see that it is 133.33 kilojoules per kilogram. Sorry, kilojoules per kilogram. And that is going to be our fuel value. In contrast, when we take the fuel density, for this example, we have 40,000 kilojoules for every 75 meters cubed of a certain product. And so when we take the fuel density, we're going to get 533.33 kilojoules per meter cubed. And so a lot of times people will wonder, well, what are the applications of this? Why would this be important? Well, for example, with rockets, a fuel value is very, very important because though a fuel may combust and be more reactive than another fuel, it might be less dense and unable to fit in certain containers, or it may be too dense, and the mass of the actual fuel will not be able to produce enough energy and lift for this mass to get off the ground. And so I wanted to kind of demonstrate this. If you guys know about Elon Musk, this is an engine that I don't know if he designed it, but SpaceX did, that uses subcooled liquid methane as a fuel with liquid oxygen, because we know that every combustion must have oxygen to take place. And so I wanted to just kind of look at this reaction and kind of show you just how incredible really this thing was. Great. Well, we're out of time here, but I just wanted to just kind of recap and remind you guys that enthalpy is a very, very important process of chemistry, and I know that as we develop the skills to understand these things, we're going to be able to understand how we can really change things in the world. And so I wanted to just thank you guys for your time, and I hope we all do well in the exam. See y'all later.